We're here with our final guest lecturer for the course. And today we have Dr. Yunzhu Li. He is an assistant professor of computer science at Columbia University, where he leads the Robotic Perception, Interaction, and Learning Lab. He is also a former instructor of CS231N, like all of our guest lecturers, and he taught the course in 2023 while he completed his postdoc here at Stanford with professors Fei Li and Jiajun Wu. His research lies at the intersection of robotics, computer vision, and machine learning, and specifically his work focuses on robot learning and aims to significantly expand robots' perception and physical interaction capabilities. In today's lecture, he'll be discussing exactly that topic, robot learning, and I'll now hand it off to Yunzhu for today's lecture.
Yeah, thank you, Zane, for the very kind introduction. I'm super excited to be here. Last time I was here giving lectures was 2 years ago, 2023. And similarly, I was going through many of the lectures. And today I'm gonna talking about some of the things that I have been working on. And also it's also a very coherent piece of this overall pictures on deep learning for computer visions. And this is specifically on robot learning. So I'll be discussing what are some of the interesting considerations, especially in enabling the robots to better perceive and interact with the physical world, and how some of the considerations might be different from some typical computer vision tasks and computer vision methods. So first of all, you guys have already learned a lot about supervised learning. The thing and the setup for supervised learning is that you have data, X and Y. X is the input and Y is a label. And you are trying to learn a mapping that maps from the input X to the output Y. There are examples you have already learned, like classification, regression, object detections, etc. And you have also learned about self-supervised learning, where instead of having labels, in this case, you are just having the data without any labels. What you are trying to do is to come up with learning algorithms that is able to extract or identify the underlying hidden structures of the data just by working or designing some auxiliary laws. Some typical example including autoencoders. And there's many other examples in trying to do unsupervised learning or self-supervised learnings on top of this mass amount of unlabeled data. And the special thing and the unique things about robot learning is that the robots has to make physical interactions and make interactions with the world. So it's not just you have the input and outputs and mapping from the input X to Y or some kind of latent representations. It's really about you are influence evolutions of the environments. So no matter what action you decide to take in the real world, the world will change as a result of that actions. And the world will give you some kind of new observations or reward, telling you how the environment has been changing and how good you are in executing certain tasks. So the goal is trying to actually come up with a sequence of actions with feedback from the environments. That is to maximize some reward or minimize some cost. And robot learning, especially in the recent years, has attracted significant attentions, both within academia and also within industries. So we have seen many startup companies, and including, for example, physical intelligence, Tesla bots or Figure. They are producing those seemingly very nice and fancy videos of robots doing a wide range of very complicated tasks, like folding shirts, like manipulating coffee beans, or trying to have this humanoids doing interesting tasks in the real physical world. So this field, like I mentioned, has attracted a lot of attentions and also a lot of investments. Here are just some examples of some recent startups in the field of robot learnings that is able to attract a huge amount of investments trying to build these general purpose robots that can make physical interactions with the environment. So obviously, not only those startups, many big established companies are also having their own robotics investigations and initiatives trying to develop their own general purpose robots that is able to make general purpose and high performance physical interactions with the environment. So for today's lectures, I'm going to give you some kind of overviews on some of the key techniques, enabling factors of the current success and boom of robot learnings. We'll start with a problem formulation. So how can we more concretely define the problems we have been building, and how can we formally thinking about the robot's interactions with the environments? So I will then discuss on the more perception sides, I will talk about the different considerations between how robots perceive the environments and how people typically consider in the computer vision community and what's special about robots' perception. Now we're talking about reinforcement learning, model-based planning, imitation learning, like also some of the recent trends on robotic foundation models, and also like using the remaining time to discuss some of the challenges we still see like lies ahead of us. So we'll start with problem formulation. So this is in general like how the problem should look like, at least in a graphical illustration. So in the middle, we have this agent. The agent is given some task objective. This task objective could be, for example, language instructions from human or some kind of objective functions measuring how good this agent is in doing some specific task. This agent is taking states from the physical worlds or some kind of environments. And the agent decides what action to take, like this AT here, that needs to be executed in the physical worlds. And these physical worlds will be updated and given this agents, this states as t+1, as well as the rewards telling the agents how good it is doing its task. So this is how the framework in general look like. So you have to be very clear on this type of formulations that consists of goal, states, actions, and also rewards. That specifically defines the problems of the robot learning like type of scenarios. It's very different from the computer visions. I would like to say like computer vision is mostly about trying to learn some kind of representations of the environments based on the inputs like high dimensional data. But for robotics, it's basically trying to solve some kind of optimization problems where you have the constraints, which is the physical world of the environments. You have your objective functions defined over your goal. And you are essentially trying to solve these optimization problems by coming up with a sequence of actions that can maximize or minimize your objective functions. So that's a key difference between like robot learning and what people typically consider in computer vision. So some specific instantiations of this problem, like for example, carpole. The goal can be balanced pole on the top of a movable cart. And the states of these environments essentially describe the physical status of these systems, which can include the angle, the angular speeds, positions, horizontal velocities, etc. And the action will be the horizontal force that is applied to the cart. And you could have the rewards where one indicating at each time step if the pole is being kept as an upright position. Some other example could including like robots locomotion, where the goal is to make these robots moving forward. And the states could include the angle, position, velocities of all joints within these robots. And the action could be the torque applied to each one of the joints. And the reward can be like one at each time. The robots like make a step forwards and also being kept in an upright positions. And also like some interesting example, including the Atari games. The goal can be complete the gaming with the highest score, as high as possible, like you can get. And the states will be the raw pixel inputs of the gaming screen. And action could be the gaming control, like up, down, left, and right. And the reward could be the score increase and decrease at each time step. And some of the more famous examples you probably have noticed like earlier, especially with the developments of AlphaGo. And the definition and the problem of Go can also be defined in similar ways, where the goal is to win the game. And the states will be all the pieces that are currently already on the Go board. And action could be where to put the next piece down on this board. And the reward could be on the last turn. If you win, you get a reward of 1. And if you lose, you get a reward of 0. And this not only applies to, for example, gaming domains. Like even with the recent developments of large language models, you can also thinking about those problems, especially for sequential generation problems in a similar manner. Or the goal could be to predict the next word. And the state could be the current word in the sentence. And the action will be what the specific next word you want to put there. And if it is correct, you get a reward. If it is incorrect, you get a reward of 0. And similarly now, you probably have already played with many of the chatbots quite a lot. And you can also define a problem similarly, where the goal is to be a good companion to the human user. The states could be the current conversation, and action that should be generated by the chatbots will be the next sentence you are given to the human user. And according to the human evaluations, we could define the reward if the person is happy, like if they are satisfied, you get the rewards of 1, and if you are not happy or neutral, you get some other rewards. And more specifically, for example, in the robotics domain, and the task could be to fold the clothes. And we want the clothes to be folded nicely. In the states is the current observations the robot is getting from this environment, which could including the multi-view RGB or RGBD observations of the environment. And the robot needs to decide its actions, like how to move its inner factors. Should it close or open its grippers in order to manipulate this clothes? And according to human evaluations, if the clothes is properly folded, you give the robot a reward of 1. And if the clothes is not folded, you give the rewards of 0. So here is actually how you want to more concretely thinking about the robot learning problem. It really is a way that allowing the agents to interact with the world. That considers the effect of an actions and also this sequential decision-making problems. That is different from what people typically consider in computer vision, which just needs to predict the outputs. And the goal, states, actions, and the rewards and the objective functions are the things you need to keep in mind whenever you are thinking about problems along this direction. So this is about problem formulation. So the question is how specific the reward needs to be designed. Like in many of the tasks, the reward can have many different type of specifications. For example, in the self-driving, the reward could be as fast as possible, or reward could be we want the passengers to feel comfortable as you are driving along the roads. So even for clothes folding, depending on the user's preference, a clothes can be folded in many different ways. Some want the total area to be as small as possible. Some want it to be as smooth as possible. There could be different types of rewards. Here I'm just talking in generic terms, if a person look at the clothes, do they think this is folded or not? But more specifically in terms of the reward design, there's actually a lot of nuances in satisfying a specific needs of a specific application. Okay, so I'll continue. So this is how we are thinking about those robot learning problems that allows the agents to interact with the physical world. Now I'm moving on to robot perception, especially in discussing how the perception problem within this robot learning domain is different from what people typically consider in computer vision. So this image again, you're actually going to see this image again and again through today's lecture. So this is essentially in the question of how we are handling the whatever information you are getting from the physical world. The physical world can give you, for example, high-dimensional RGB observation or RGBD observations. It could also include some other sensory data like tactile sensings. And this robot perception problem is essentially trying to distill or harnessing some structured knowledge from those high-dimensional data that is useful for the robot to do the downstream decision-making. And essentially, the question we are trying to tackle is trying to making sense of this unstructured real world. And the real world can be very messy. So essentially, the observations the robots are getting from the environments can only contains incomplete knowledge of the objects and the environments. There could be occlusions. There could also be errors from the sensory data. And the imperfect action may also lead to failure. For example, the robots can try to grasp some objects, but their grasping behavior may not always be successful. Sometimes you accidentally drop that object, which will also cause evolutions and unexpected changes of this environment. They will also need to have this perception system that is able to handle those scenarios. And also, this environment can change. It is dynamic, consists of not just rigid object, but deformable object, clothes, robes, granular medias. There could be other agents like dogs or other kids or other humans that are also in the same environments, messing up with the world. And your perception system needs to be able to cope with all those kind of changes. So that is why, in the robotics domain, people typically not just working with camera data. They'll try to add as much sensor as possible to the robots as long as they can provide some useful informations. It really considers, for example, the tactile sensing, the audio information, the depth information, etc. And typically, we'll have to design a systems that is able to put all the sensors together, that allows them to complement each other. Whereas audio information might tell you things about the physical context, and the tactile information might tell you about whether a grasp is stable or not. And the camera information tells you about something that is more on the higher level, on the grand scheme of things about the overall state of this environment. So how these sensors can be composed together and work together is very, very important to design a capable robotic system that are working in the real physical world. And besides the numbers of sensory modalities, very important difference between like a robot vision and computer visions is trying to really understand the effect of an actions and also the affordance of this environment. On the left is a very typical examples you have already seen in computer vision, which is trying to do instant segmentation. What you are given is this 2D image. You are segments different instances from this 2D image, like by drawing like a contours over this 2D pixels. But what's different in the robotics domain, for example, on the right? The robot can, for example, given one object, and this object seems to be maybe just one object, or maybe a lot of pieces that are, for example, stacked into each other. So the robot has to know, like, what type of actions will allow it to have better understanding, better perceptions about this environment. Is this one piece of object or multiple pieces composed together? So the robot should come up with actions like perturb and actively interact with the environments for the robot to get a better perceptions about the states of this environment. So that is why a robot vision is embodied, active, and also environmentally situated. By embodied, what we mean is robots have this kind of physical body that is directly experiencing the physical world directly. Their actions are part of a dynamic with the world that have immediate feedback on their own sensations. And active, meaning the robots are active perceivers. It knows why the wishes to sense and chooses what to perceive and determines how and when and where to achieve that perception. You can move your head around. You want to know like what's behind this table. You can just move around to see what's behind the tables. So this is the active parts, which is different from what people typically consider in computer vision. It are mostly like work with the passively collected data sets. The third point is about situated. As the robots are situated in the world, they do not deal with abstract descriptions, but with the here and now of the world directly influencing the behavior of the systems. Our robots really have to understand, especially in closing there's perception and action loop. It sees the world and understanding its goals and be able to act in the environments upon its perceptions. Sometimes the robot don't have to know the full state of environments. For example, if I'm buttoning my shirt, I only have to know the local regions near that button for me to button that shirt. So some of the perception has to be tightly coupled and co-designed with the task and the downstream decision-making systems for the robot to focus on the relevant region or task-relevant regions of the environment to be properly close this perception and action loop. So this is about some very specific considerations and how robots' perception might be different from what people typically consider in computer vision. I will starting to discuss some of the algorithms that not only allow the robot to see, but allow the robot to act in the world. And we'll start with reinforcement learning. Remember earlier we have seen this image. The robot has to act upon this environment and get rewards from this environment. So one very typical ways of trying to solve this optimization problem is allow the robots to interact with the world as extensively and as massively as possible. You just collect all the experience data and do this type of trials and errors. Allow the robots to understand this action leads to higher reward and that action leads to lower rewards. And we can pivot the agent's behaviors towards the actions that give the agent some higher rewards. So this is the general ideas of reinforcement learning. It's really a way to allow the agents to constantly interact with the environment and do this trials and error to maximize the reward or minimize the cost. And here I also want to be a bit more specific in discussing the difference between reinforcement learning and supervised learning. So this is a typical framework of how reinforcement learning look like. You have the environments. Environment gives the agent some states. Agents generate actions. The environments give the agent the feedback, which is the rewards. And the environment will change, where the environment will give the agent the new states as t+1. And it is essentially a sequence, like a temporal sequence on the temporal domain, where the agent has to make these sequential decisions. And here is a typical image, typically look like for supervised learning. So you have the data sets. The data set will input to the model this X, and this model will generate the prediction Y. And you will be able to calculate the loss according to the model's predictions versus the ground truth from these data sets. So this is a typical setup of supervised learning. And some of the key difference between reinforcement learning and supervised learning is that the environment might be stochastic, or the same actions, the environment might change in a different manner. Let's say if you are pushing a box forward, depending on the distribution of the supporting force, the same exact actions can potentially lead to the box rotating into different angles. Meaning there can be uncertainties and stochasticities in the environments that will lead to a stochastic behaviors of these environments, which will also give these agents stochastic rewards, where the same action may not always lead to the same rewards. So this is very different from supervised learning. We are dealing with an uncertain dynamical system. The second is about the question of credit assignments. So for supervised learning, you give the inputs, you predict the outputs, and directly calculate the loss. You directly know what are the mistakes and what are the errors you are making by making a specific predictions. But in the reinforcement learning or sequential decision-making domain, the rewards can be delayed. Meaning if you play the game of Go, only until the very ends of these episodes do you realize you were winnings or you were losing. And that rewards 0-1 is because of some very, very early steps, maybe even the first steps or some steps during the middle of the games. So how to properly assign the credits you are getting along this sequential decision makings towards all the actions is also another very tricky and important questions people hope to answer within reinforcement learning. The third thing is the non-diffusion abilities of these dynamical systems. For example, for supervised learning, you have the inputs, you feed the input through the model, you get outputs, you calculate the loss. So everything along this process is differentiable. So you can directly gather gradients of the loss functions with respect to the parameters within the model. But that's typically not the case for reinforcement learning, where the environments can oftentimes not differentiable. So how to properly gather gradients of the rewards with respect to the actions can be tricky. Sometimes people have to rely on a massive samplings to do those type of zeros order estimations of the gradients for you to do proper learnings. That's also is another difference. The last difference is about this non-stationarities of these scenarios, where the evolutions and the states of the environments is really a result of your actions. For supervised learning, no matter whatever you predict, it doesn't influence other data points you are getting from these data sets. But your actions will influence the next stage you are getting in this sequential decision-making problems. That is also what makes this kind of reinforcement learning problems a little bit more nuanced than supervised learning. So here are some more specific examples. For example, playing these Atari games, like I mentioned earlier. The goal could be to complete the games with the highest score. And the states would be the raw pixel inputs from the gaming screen. And the action could be up, down, left, and right from the keyboards. And I'm trying to the reward are the score increase and decrease at each time step. And some typical algorithms within this domain either lies in the field of, for example, Q-learnings or, for example, policy iterations. Here's one example of trying to learn this Q function. Q function essentially measures the discounted, expected, future accumulated rewards, when you apply a specific action A at a specific state S. And you will be able to get these Q functions through interactions with these gaming environments. And after you have learned these Q functions, you can evaluate, for example, what are the Q values you are getting by applying different actions. In this case, there's left and right, ups and downs, so there could potentially be 4 actions. And given these 4 actions, you can look at their Q values and just execute the actions that give you the highest Q values. So that is what allows you to do this type of decision makings in this domain. So, because today we are going to cover a lot of materials, so we won't go into the details of the reinforcement learnings. But some of the current state-of-the-art reinforcement learning algorithms, including SAC, like soft actor critics, and also PPO, like proximal policy optimizations. So if you are interested, you are very welcome to look at those algorithms in details. There's a lot of open source implementations and tutorials online. But here I want to highlight to you some of the results you could potentially get by going through this reinforcement learning, specifically Q learning process. This is developed by Google DeepMind. That is trying to develop these agents that is trying to play the game breakouts in this kind of Atari world. So just after 10 minutes of training, the agent can already touch the ball, but oftentimes can still missing the ball quite often. And after some more times of learning, for example, 2 hours of training, and the agents can control this kind of paths in a much more reliable and consistent fashion that can nearly all the time can catch the ball and be able to constantly getting more and more rewards by bouncing it back. And after 4 hours of trainings, something that's interesting happens, where the agents come up with actually a novel strategy, which possibly is not known to many of you. That is trying to bounce the ball back to create a tunnel on the left side of this wall. And then it will push this ball on the upper side of the wall to do this very efficient reductions of those bricks. This is a type of strategy that can be discovered by reinforcement learnings. So this is what's nice about reinforcement learning, meaning you allow the agents to do very extensive and comprehensive exploration and interactions with the world. And it is totally possible for this reinforcement learning agents to discover some strategies that are better than even the best human players. A very typical examples would be the game of Go. So when AlphaGo came out in January 2016, it was also about the time when I was trying to decide what type of research directions I'm gonna go. Before that time, I was just working on deep learning for computer visions. But when AlphaGo came out, I'm I have to work on this kind of decision-making problems. So that's when I started to touch upon reinforcement learning, imitation learning, and all the way until now to do robot learning that allows the robots to do physical interactions with the environments. So I wasn't satisfied with just working with the passively collected data sets, but we really want an agent that can do active interactions with the environment. So the questions was how does specifically this Q functions works? So you can see this Q take as input the state S and also the action. And this theta would essentially be the parameters of this Q functions where the Q is instantiated as a neural network. In this specific case, like I mentioned earlier, the states is the raw pixel inputs that directly getting from the gaming screen. So the inputs could be this kind of 4 steps, 4 frames that directly inputted to this Q function. And if you are dealing with images, a very a straightforward way of instantiating this Q function is to use convolutional neural networks. So you have convolutional layers shown in this kind of orange blocks, and then you'll be able to go through these fully connected layers to directly derive this a Q value. And in this case, because there are 4 discrete actions, in this case probably just left and right, but let's say there's 4 discrete actions, up and down, left and right. So you'll be able to have different Q value estimations that is the result of this specific action A. And that's how you can use these Q values to make decisions on what action to take that is the most effective at maximizing this Q value. Does that answer your question? Mm-hmm. Yes, this is when AlphaGo came out. And obviously, since then, there has been a lot of developments and evolutions in making this type of gaming agents better and better. So then later, there's AlphaGo 0. That is essentially a simplified versions of AlphaGo. They're no longer using any imitation learning to do any initialization, and is able to beat at that time the number one player Koji. So this is actually one lessons people learned inside this AI communities, which you can call it the bitter lesson from the rich Sutton, where sometimes you want to find the simplest recipes. that is the most and best compatible with the scaling. You want to leverage the scale, like the power of scalings. And sometimes like making this method simpler will actually give you better performance by like making it more compatible with whatever infrastructure you can use for scaling things up. And then later, they develop AlphaZero that is able to generalize the same set of algorithms into not just chess, not just Go, but other games like chess and shogi. And then they design like a Mu zeros that's like not just like do this kind of model-free reinforcement learning, but it's able to learn latent space dynamics models to plan over that give you like even better performance. So for this specific domain, like I would say, especially in the gaming developments, that really empowers a lot of like design and developments in how people can do better and more sample efficient and more scalable design of those reinforcement learning like agents. And in November 2019, like Lee Sedol, like who was beaten by AlphaGo, announced his retirement. And he realized it's just not possible, like at that times, for any human players to beat the best like Go, like AI agents out there. And obviously, since then, there has some been other like more complex games like StarCraft and Dota that shows that as long as you put enough compute, as long as you have like a good, like a very well designed like algorithms and infrastructure for you to do the reinforcement learning, you can get very, very good performance in games that are actually noticeably and orders of magnitudes more complicated than the game of Go. So I would say like if you have a game, like a reasonably designed games, like there's like a very legit chance, like if you put as the sufficient resource, you can have very, very powerful gaming agents. So not just in games, people have also been developing these reinforcement learning algorithms and agents that can work directly in the real physical world. So this on the left is a work from ETH that was published in Science Robotics 2020. That essentially changed my mind about how useful reinforcement learning can be for real physical robots. Because before it was just mostly games, like you could argue. In games, like there's a lot of, you can just like spawn as many games as possible. But for the real world, there's always like sim to real gap, where you are training on the same game, you are also testing on the same game. But for robots, if you train on a simulation, like how much does the sim to real gap matters for the agents to generalize to the real environments? And this paper really convinced me that sometimes the sim to real gap just may not matter that much. So we are not simulating the bushes, we are not simulating the snows, but the agents that's using reinforcement learning, that training simulation, can give you some very, very robust performance in the real physical world, like snows and very, very slippery like a surface. On the right is a very recent video released by Yunzhu Li that shows just another levels of like dexterities for locomotions that can do this kind of sim to real transfer, allow these robots to do like very, very crazy and dynamic behaviors that can navigate into some very rough and challenging terrains. I would say in the domain of robot locomotion, it is close to be a solved problems. And the solution to these problems is exactly reinforcement learning. So this is about locomotion. So other domain is about manipulations, where the robot has to manipulate the objects in the real physical world. So in 2019, when OpenAI was still like a touch upon like robotics, they designed the systems that are trying to do dexterous manipulations of Rubik's Cube. They are able to do the reinforcement learning in simulation and do sim to real transfer that allow this kind of robots to like solve this Rubik's Cube. But one caveat is that their success rate is very, very low. Like, although this video seemed to be very beautifully done, but their success rate was very low. And if you really look at the papers, they only tested a very limited amount of trials. And given that number, possibly the reliability is not very like satisfying. But still, like since then, people have been able to like extend upon this dexterous manipulation problems and allow the robots to do enhanced dexterous manipulation and reorientations of different types of objects and into different like target configurations. It's all thanks to the developments of reinforcement learning. But we can see until now are examples in locomotions and in hand manipulation. It doesn't really solve the problem, for example, if the robot can just fold the clothes for you or doing the laundry for you in your home. Like for manipulation, it's still in this kind of very like isolated domains, like working with this kind of isolated like environments. So this is actually some of the key challenges and bottlenecks of existing like a model-free reinforcement learning. It is mostly learned from the trials and error with the environments, and it requires extensive like interactions with the world. For example, for the AlphaGo Zero, like it actually learns from 3,000 years of human knowledge in 40 days, which is amazing. But like it still requires like many like years of computation, like years of like equivalent computations for the agents to learn. If in domains where there's like a huge symmetrical gap, and if you want to do the reinforcement learning in the real physical world, that will be a huge bottleneck for learning this reinforcement learning agents very effectively. And also, of course, if there's symmetrical gap, if you only can learn the model in the real environments, there's a lot of like safety concerns. For example, here is an example of showing this kind of learning progressions of an agent that is controlling this humanoid robots to move forwards. You can see like during this learning process, although at the very end, the robot is able to like move forwards, but there's a lot of like very weird behaviors that you can totally imagine if you apply these agents on the real physical robots, it will like fail catastrophically. And it also have like very limited interpretabilities, and sometimes it's very hard to correct things when things go wrong. And like one interesting thing, if you're really thinking about how humans learn to interact with the environment versus like pure reinforcement learning, you realize that we humans have a very intuitive understanding of these environments. We can imagine how the environment is going to change if we apply a specific actions. So it's exactly these predictive capabilities that allows we humans to plan our behavior in achieving some specific targets. And this predictive capabilities is also actually learned from we humans' physical interactions and everyday experiences with the real physical world. So going beyond the reinforcement learning, the next topics I want to discuss will be how we can indulge the robots with similar capabilities in imagining the effect of their actions and to do model-based planning. For these specific examples, we have simulation. Typically, the simulation people use would be, for example, Isaac Gym or Isaac Sim developed by NVIDIA. And there's essentially a bunch of like rigid body simulations where the robots like just touching this kind of like a polygon type of representing like a representations of the floor. It is not simulating, for example, the bushes. It is not simulating those snows. But what people do is to randomize the simulated environments a lot. They randomize the friction, the geometry, and many other physical parameters inside these environments, such that people will assume whatever you encounter in the real physical world is just one data point within the distributions you randomize within your simulation. So if your policies can be robust, like robust in controlling these robots within that distribution, and if the real world is just one data point within that distribution, the policy can generalize. And so far, at least from this empirical evidence, this type of assumption actually holds, and the policy actually works very reliably and robustly in the real physical world. So the question is about like what is actual command. So actually, in many of the existing demos, there can be a person providing high-level commands to the robot. For example, which direction should the robots like walk? Should the robots like rotate in place or just still like keep walking forwards? Conditioned on that high-level actions provided by human, the robot has to decide this kind of low-level actions. The low-level actions are typically, for example, the joint torque that applies to each and every one of the joints on top of these robots. So that is how this typically looks like, meaning humans give high-level commands, condition on high-level commands. The robot has to use this policy to decide this kind of low-level actions, which is instantiated using joint torque. So like I mentioned, one biggest lesson I learned from these lines of work on locomotion is that the simulation doesn't have to be perfect. As long as you randomize enough, you can generalize very robustly in the real environments. But such lesson hasn't really been generalized very well in the manipulation domain. So in the manipulation domain, how accurate the simulation needs to be and how much does the symmetry gap matters is still a research question people hope to answer. So I can give you one specific example. If in the simulation, you are pushing a box forwards, if in simulation the box rotates for 10 degrees, but in reality it rotates for 12 degrees, it may not matter that much. But if in the real world, your grasping was successful, but in simulation, the object just flies away because of some kind of numerical issues, or if the object slips away between your fingers, that's problematic. So there are regions where symmetry real gap matter. There are other regions symmetry real gap may not matter that much in the manipulation domain. And people still are trying to answer and trying to understand how symmetry real gap can happen and what are some of the most important recipes and characteristics that this simulation needs to have for the most reliable symmetry real transfer. So if I understand your questions correctly, you're asking there are still a person providing high level commands to the robots. So your question is, can the robot come up with better plans than a human? So I can actually give you a more nuanced perspective. Although many of these videos seems very nice, there is a human operators operating the robots to choose which route to go. For example, what people typically do is, for example, let's say there's some kind of rough terrains or some pile of rocks, and the humans can actually try to command the robot to going forward, trying to climb those kind of rocks. If that fails, humans can actually provide some other high-level commands to get around this pile of rocks. So there can be some kind of learning also on the human side in understanding the capabilities of those robots. So this is also why some of this video can actually looks very nice, because humans select the routes that the human knows can show the limits and also the capabilities of this kind of low-level controllers. And how to do that autonomously is actually a very interesting questions people are also doing research upon. So then I'm gonna continue. So I've discussed some of the successful examples and power of reinforcement learning, and I also discussed the limitations of reinforcement learning. And we still haven't really seen very, very successful and wide-scale deployment of reinforcement learning in manipulation yet. And we humans not just learn from trials and error, we actually build this type of internal model. So we're asking the question, can we actually learn the models from the robot's interactions with the environments and using that model for the robot to do better physical interactions? So specifically, what we are touching upon, again, back to this figure, is how we can learn and approximations of the real physical world. And how can this approximated physical world that runs on the virtual domain can help guide the robot's actions and decide what action to take in the real physical world. So let's say if you already have the model, for example, let's say you have already learned the models like we humans have in our mental environments. We can predict, given the current state as t and also the action t, how the state of the environment will change into states t plus 1. And then we can use this essentially as a forward model, given the current state and action predict the next states. So what actually is the problem for us to do the planning, which is essentially an inverse of this forward model, where the planning is to give the current state and the target states, and you come up with the action that can allow the robot to achieve the target states. From a given current state showing the blue dots, we have the targets showing the red. We can have maybe some initial guesses of how the actions might look like. And our model, our approximated learned models, will be able to predict the sequence of the evolutions of the states, which is shown in this green trajectory. And then we can measure the distance between these green dots and the red dots and back propagates or doing optimizations using the gradients of their distance with respect to all the actions along their trajectories to do this type of optimizations in order to know what actions can guide us to getting us closer to the targets shown in the red. And obviously the model may not be accurate enough. So we typically only execute the first actions and we obtain the new states from the environments. And we can re-optimize the action sequence using gradient descent or any other optimization technique you use to do this trajectory optimizations. And one of the key benefits, especially recently with the development of GPUs and also neural dynamics model, is that you can use the GPU for parallel and simultaneously sampling to allow you to do large-scale sampling and optimizations of those action sequences, which is actually quite efficient. So given this a general framework, you have the model, which is this kind of forward process. And you can always use a kind of forward model to do this inverse optimizations to come up with the actions that can get you closer to your target configuration. And one of the key questions has always been, what should be the right representation of the environment? What should be the right and most effective state representation is? And how we can learn this model based on this state representation. And over the years, there has been many different investigations on choosing or investigating different type of state representations. Some earlier work including how can using, for example, just 2D images as the representation of the states and trying to learn pixel dynamics meaning how the image might change if you apply a specific actions. This is a work called Deep Visual Foresight, which set up some of the initial works in the whole domains of like word models. And by learning this kind of pixel-based dynamics models, people can come up with strategies that is able to, for example, minimize the distance between the current observations, and some can rotate objects and pushing the objects around in order to achieve the targets shown in green and the current state is shown in red. So this is about like a pixel dynamics. And what people can also do is to use like key points as a representation of the environments to learn like a key points dynamics models. And here, like what we can do is to track the movement of the key points on top of this box over the 3D space, and also learn a dynamics model of those key points as a result of some pushing actions. And then we can allow the robots to use these forward predictive models to plan the robot's behaviors in order to track some specific trajectories in order to push this box to achieve a target configurations. So besides using key points, so what if you are encountered some objects with even higher degrees of freedoms? So if you go like one level finer, you can also represent those objects using a set of particles, essentially a set of points. Here, like, which is actually a work, that was done when I was here, like, as a postdoc, where we're representing this pile of granular pieces using a bunch of particles and trying to predict how those particles will move around if you apply a specific actions. And this forward model can allow the robots to do this inverse decision makings that handle a wide range of granular objects of different like granular sizes. And we come up with strategies that can gather those pieces into the target region shown in the bottom right like a corner of each like a segment. And the same model with like a good feedback from the environment allow the robots to correct from the model's error and come up with strategies that can be very reliably aggregates all the object pieces into the target region. And obviously, this model not just can generalize to like a different like a granular pieces of different granular sizes. It can also change to different target configurations. Here, you will very quickly realize what the target configurations are. The robot has to come up with a strategy that to do non-trivial redistributions of the granular pieces. And after the redistribution, it has to align the fine-grained details with the target's like shape in order to accomplish this like a pile rearrangement tasks. The task here is actually to rearrange these granular pieces into different letter shapes, all the way from letter A to letter Z. And with this kind of forward models, we'll be very successful in coming up with a sequence of strategies, of course, with feedback from the environments, to allow the robot to rearrange this kind of object pieces into the target regions. And this is actually a highly non-trivial task. And going beyond that, we are also have this like a subsequent work, which I was also involved and done when I was here at Stanford. And we designed this kind of dumpling making robots that is actually equipped the robots with 15 different 3D printed tools. We have 4 RGBD cameras looking at the environments to do a reconstructions of the geometry of this dough. And the robots will have to decide what tool to use and what action to take in order to get this dumpling into, getting this dough into a dumpling. And the key enabling factor is also this like forward predictive models represented like using particles. Where here, the red dots are representing the shape of the tool and the blue dots are representing the shape of the objects. The first row is our model's open loop prediction. And second row is like what actually happens in the real environments. So this learned model that directly learns from this real world interactions can very accurately predict the change of the shape of the dough when using different tools applying different actions. And in the end, allows us to have this integrated system that can make a dumpling out of a dough. What's interesting about this video is there's a person constantly perturbing the robots from doing its job. The robots will take the real-time visual feedback from this environment to real-time understanding the shape of the dough, and then using the current observations and also the learned dynamics model that predicts how the environment is going to change, how the dough shape will change if you use a tool to apply a specific actions. And based on this forward model, it is making this inverse decision. This decision is happening at 2 levels, both at the high level, which is to decide what tool to use, which is a task level decision making. And given these tools, the robot is also have to make like a lower level, like a motion level decisions in deciding what specific action to take in order to progress into the next task stage. Humans are just so annoying, adding pieces, folding the dough. The robot is very robust to this external disturbance in continuing its progress in doing the task. Here's what's interesting. After the robot cuts a circle, the humans shows no mercy, destroy everything. The robot knows you actually have to start from the very beginning, like redo the task from the beginning in order to progress with this kind of task objective. So this really shows the patience and also the robustness of our systems with this type of external disturbance. And all of these capabilities is enabled by this kind of neural dynamics model that predicts how the shape of the dough will change if you apply a specific actions. In the end, the robots will place the skin on top of this dumpling clip and move this kind of fillings on top of this dumpling skin, and using a hook to close the dumpling clip in order to use this general purpose robots equipped with 15 general purpose tools to make a dumpling out of a dough. So this is about like how we can learn the model and how that model can be useful for downstream like model-based planning. So for this specific case, like if we want to describe it more rigorously, we are not using reinforcement learning. Like we just learn the model and using that model to do planning. Although the plan can be distilled into a policy that can be executed in the real environment in a more efficient manner. But some people also call it model-based reinforcement learning. Decide which background you are coming from. So you can either call it like model learning and model-based planning. You can also call it model-based reinforcement learning. But the key idea is you want to learn the model from the robot's physical interactions with the real physical world, and using that learned model that is very effective in helping the robot to decide its behaviors to like progress with the task objective. So in this specific case, it is the high-level planning and low-level decision-making is done by two different models. So over the high level, we are given the current states, like current observation of the environments and the targets the robot is able to achieve. It is essentially a classifier. It classify which tool to use. And conditional on this classified like tool label, there's a low level like policies that decides what specific action to take in order to like progress into the next task stage. Very good question. So back then this work was done in 2023. At that time, vision language model wasn't like very powerful. So at that time, like what we did was to allow a human operator to do the data collection and demonstration of the task for 10 times. We use that data to train this kind of classifier to classify what tool to use. That allows us to actually jump back and forth over this chain. Like I mentioned earlier, after the robots cut a circle, the human destroy everything. The robot knows to jump back to some earlier stages, like that fits to its current observation in order to like do the proper like recovery from the external disturbances. So in this specific case, like what we have been doing is a combination of sampling-based trajectory optimization versus like a policy learning. So what we have been doing is to give the current states of this dough. We have our like forward predictive models. We'll be able to sample a bunch of actions and sample a bunch of tools to like predict like what is the evolutions of the shape of that dough. And then we'll compare the model's prediction with the targets like we hope to achieve, which is similar to what I showed earlier. For example, our model predicts the shape of the dough will go into this green dots, but the target is this red dots. We are comparing their distance. And then that allows us to select the most effective actions that can get us to the target to be as close as possible. And we can do a lot of samples like this. But sampling during the test time is very time consuming. So we do this type of sampling in an offline fashions, which give us a data sets. And we can use that data sets to train a policies that can be inferred at a very, using a very short period of time to do the inference during the test time. There is still a neural network as a policies. Yeah. Although that policy is learned by distilling from our models predictions over a huge amount of samples. For this specific work, there's no physics-based simulation at all. We actually have a baseline that uses a state-of-the-art deformable object simulator, which is called MPM, Material Point Methods. What we realize is that even if we do very extensive system identification, like estimating the parameters of those physics-based deformable object simulator, the identified model is noticeably less accurate than the model that directly learned from the real-world interactions. Like I showed earlier, for example, the first row is our model's open-loop prediction. The second row is the ground truth. Our model's prediction aligns very well with the ground truth, which is just much more accurate than whatever physics-based simulators out there. Okay, so if there are no more questions, I will continue. So what we have discussed is this kind of model learning and how this learned model can be effective for the downstream like a model-based planning. And the next category of algorithms is imitation learning. So just to recap a little bit, we discussed reinforcement learning. That is directly learning the policies by doing trials and error with the environments, which has a lot of troubles, for example, the sample efficiency, the safety concerns. And for the model learning, what we have been doing is actually force back to the category of supervised learning, where you have the evolutions of the environments. You use that data to do supervised learning, to train this model, and using this model to do model-based planning. And instead of just using supervised learning to train the model, people are also asking, can we do supervised learning also for the policies? This is a general idea of imitation learning, meaning can we have a big data set that shows how a task needs to be done, and using these data sets to train this kind of policies. I'm showing this figure again. This is trying to learn this kind of policy, taking the states as inputs that predict the actions. And all of this kind of learning signals and learning procedures are done through a large-scale collected data from human demoing to the robots how a task needs to be done. So learning from demonstration is, of course, not new. It has been investigated for decades. It's also constantly how we human is actually learning to perform a lot of physical interactions or social activities in the real world, since we are very, very young. So one of the most earlier classic imitation learning algorithms is called behavior cloning. It's essentially trying to learn this kind of mapping. They map currently from this observation O into the action A. And this policy is represented using this function pi parameterized by the theta. So one of the key issues for behavior cloning is called cascading error. Because like I mentioned, the key difference between the robot learning or agent's interaction with the environment is it is a sequential decision-making problem. It differs from a typical supervised learning in the typical computer vision domain in that your error can accumulate and be amplified over time. Let's say at the very beginning, you made a very small error. That small error can lead to a state that is slightly deviates from the distribution of data used to train your model. That will lead the policy to make an even larger error. And this error will be amplified over the temporal horizons that leads to a trajectory that can deviate quite a lot from the demonstration trajectories. So that's the typical issues of behavior cloning. So that's why, oftentimes when people are trying to make imitation learning work, people will follow this type of pipeline, where on the top, we have the demonstration collected by the experts. Then we'll use that as a training data to do supervised learning to train this policy. And we'll roll out the policy in the real environment and observe those failure cases. And we either collect additional data or provide corrective behaviors that allows this data sets to not only contain the initial demonstrations, but also those corrective behaviors that gets the errors from the policies back to the canonical trajectory or get back to the trajectory that can still successfully accomplish the task. So this is actually a typical life cycles we are trying to develop any imitation learning agents or imitation learning algorithms in the real physical world. And along these lines, because if people do this kind of imitation learning, there's not very explicit definitions of what the task actually is. The task is implicitly hidden within those demonstrations. So there's a class of algorithm called inverse reinforcement learning, where on the left is what people typically thinking about for reinforcement learning, whereas on the right, where people are trying to use this inverse reinforcement learning to summarize the rewards from your demonstrations and be able to use that reward to do typical reinforcement learning to learn this kind of algorithms. Some of the earlier success examples were actually also developed at Stanford by Peter Bill and also Yunzhu Li. It allows them to control helicopters to do some very, very crazy behaviors. And this is actually a very old work. And be able to achieve this type of agile and effective behaviors on this real physical helicopters is very impressive at that times. So this is the power of learning from demonstrations and using that demonstration to summarize the rewards and in connections with reinforcement learning. This is what we are able to achieve. So obviously over the years, people have been making the imitation learning algorithms more and more effective, especially in connecting with for example, energy-based models. So instead of learning this kind of explicit policy shown on the left, they directly do the mapping from the observation O to the actions. People are coming up with the kind of implicit policies that takes the idea from energy-based models that direct taking the observation and actions to predict the score, and using this kind of like an energy-based model to do inference to get this kind of predicted actions A has, allows the robots to handle demonstrations that are very multimodals or handle scenarios where the optimization landscapes may not be very, very smooth. And the robot is able to come up with this kind of strategies, like distill these policies from the demonstrations in doing this kind of content-enriched manipulation tasks. And now I'd like to say, like, some of the very recent success of robot learning as a whole is the results of this work called diffusion policy, which again is also taking some of the advances in the community of generative models. For example, this one, like for the implicit behavior cloning, people are drawing inspiration from development of energy-based model. Energy-based model is a type of generative models developed in the deep learning community. And there's another class of like more powerful models in the deep learning community is called diffusion models. And people are also trying to use the diffusion models to use it as a policy function class to allow the agents to also like inherit the benefits and the properties from those diffusion models. So this work was originally done at Columbia. That's where I am right now. And the leads, like a PI of this work now come to Stanford. So you can see like many of the work I selected has a lot of like roots like here at Stanford. Like she's currently like at the WE departments at Stanford. And this policy really shows some like a very diverse set of capabilities, allow the robots to do not just like planar pushings, but many like fine-grained like manipulation tasks. Not only pick and place, but for example here, spread butter on top of this bread, and also like scrambled eggs, also peeling the potatoes and sliding the books. So it really shows that this type of recipe, where you collect a bunch of demonstrations and using the best policies, like learning mechanisms, you can get a policy that works in the real physical world in a very, very efficient manners. Meaning, you collect the data in the morning, you train the policy in the afternoon. You can have working policies working in the real physical world. So obviously, there's a lot of caveats in how reliable your policy is and how generalizable your policy is, how diversified the initial configuration can be for the policy to still work very robustly. But still, imitation learning is the most efficient way for you to get a policy that can do something interesting in the real physical world. And for the policies to be very effective and robust to the real world variations, this type of iterative like data collections will need to be in place for the policy to cover those kind of like unexpected behaviors or some kind of deviating behaviors. So this is about imitation learning. So any questions? Okay, so if there's no more questions, I will use the remaining time to discuss some of the recent developments that drive all the craziness about robot learnings, which is like robotic foundation models. And of course, like this is a very involved domain. Actually, for each one of these items, you can actually have a course around them. So like for today's lecture, I'm just like skimming through them very, very quickly. I only tell you the gist, like the high level, like knowledge you need to get by looking at those terms. And for robotic foundation models, it is a type of models that is very similar to like reinforcement learning or imitation learnings in their function class. There's no explicit representation, for example, of the states or this kind of model. For example, this robotic foundation model doesn't learn the model of the environments. It is still a policy that map from the observation and go into the actions. That's still like represented, can be very nicely represented using these figures. So you have this agents, which is a policy that taking the current state and also the go as inputs, that is trying to generate these actions that can be executed in the real physical world. But you might say that this is very similar to imitation learning and reinforcement learning. So what's special about these robotic foundation models? So this is actually all rooted back to all the developments within the foundation model domain, especially those language-related foundation model and also those vision language-related foundation models. Meaning, it is a policy, but it needs to generalize much better than a policy that just works for one specific task. Like here is actually my definitions. I'm drawing analogies from the current developments of vision language models, meaning their outputs may not always be the perfect one, but to always generate something reasonable as you prompt this kind of foundation model. So what we hope to achieve with this robotic foundation model is the synthesized action may not always be the optimal actions as conditioned by the observation and the task, but the generated trajectory will always be beautiful and reasonable to execute in the real physical world. Like beautiful meaning it shouldn't use any like jiggling motions. It should be smooth and continuous. Reasonable meaning you should listen to the language instructions you are given to the robots. So obviously there are also many different names describing exactly the same things. Some people call it vision language action models like VLAs. Some people call it like a large behavior models. But in the essence, they're all describing the same thing, meaning this policy. Taking the observation and language instructions or whatever like a task specification is trying to generate the actions that generalize widely across a wide range of scenarios. So this area is actually quite noisy. Noisy meaning it's very, very like hard to quantify the progress of different kind of robotic foundation models. Because you are calling it foundation model, what does that mean? That means you expect this model to generalize like very broadly over a wide range of scenarios. If that's your expectation, you actually need significant evidence to show it actually generalized broadly. So that's why evaluation and quantitative measurements of their progress is very challenging. But still, by looking at their empirical videos, you can still see a lot of very interesting and concrete progress over the past few years. So a lot of the earlier investigations starts with RT1, which was released in the December 2022. And since then, I would say maybe roughly every half a year, there's a new model, for example, RT2, RTX, OpenVLA, and some of the recent ones like Pi0 that is making concrete progress along these lines of developing more and more generalizable robotic foundation models. And actually, this year, there's a boost. There's a huge burst of a lot of foundation model like Helix, HiRobot, Gemini Robotics, Pi0.5, etc. So there's a lot of investigations and also investments in this domain in not only capital investment, but talent investments in developing better and more generalizable robotic foundation models. So due to the time, I clearly cannot go into the details of all these models. So if you are interested, I actually gave a tutorial 2 months ago at AI, specifically describing and discussing some of the models along this axis. If you are interested, please go and watch it. And for today, I will mostly give you a high-level overview of what actually is essentials for this kind of foundation models and what it actually looks like with examples from Pi0. So Pi0 was first released in October 2024. I think this is the word that convinced me that this type of robotic foundation model can do some very reliable textual manipulations in the real world environments. It can handle cloth folding and box folding and many other different types of manipulation tasks at a very reliable manner. And here's how the framework actually looks like on the high level. On the left is datasets. So for any model to be called foundation model, it needs a field for that foundation model, and that field is data. So they aggregate a lot of data, both within academia and also data collected by themselves across many different embodiments where the robot is doing some kind of interesting and useful task in the real world environments. And they use this data to do pre-training. And one important caveat of this pre-training is this starts with a pre-trained vision language models. The vision language model that's already trained on vast amount of a vision language related data that can naturally adapt those kind of semantically knowledge from those models. And together by doing co-fine tuning, what they call co-fine tuning, using both the objective for action predictions and also the objective adapted from those vision question answering, those type of tasks, you will be able to first preserve the semantic knowledge within those models, but at the same time, you can predict the robot actions. And this is the pre-training stage. A very important design for many of the existing robotic foundation models is called post-training, which is also inspired by many of the developments in the large language model communities, where you have this base model. base model can give you some reasonable baseline performance, but you really want the performance to be very, very good on a specific task. You actually have to collect task-specific data to fine-tune the models, do post-training on the data for that specific task for the performance to be satisfying. So they are evaluating their whole systems over 3 different categories. The first one is to directly using their base model. And their base model can already be good enough for some very simple in-distribution data. The task is actually the task that might have already been encountered during the pre-training stage. If for in-distribution task, but slightly more complicated, they can do post-training to allow the base model to further improve on those in-distribution tasks. And for unseen tasks, typically you have to do post-trainings by collecting those task-specific data and fine-tune your pre-trained model on these tasks for it to be performance. And this Pi0 model is actually open sourced. And you can just download the checkpoints. My lab, the students in my lab have already been starting to playing with this, their models and trying to do post-training. And we are starting to see some very promising, results. So if you are interested, highly encourage to try it. That is a very good question. So you are essentially asking about the efficiency of the existing robotic foundation models. So there's a lot of reasons why the policy is actually slower than humans. One of the major reasons is actually adapted from how the data was collected, how the demonstration data was collected. Typically, for many of these scenarios, the demonstration data was collected by human, teleoperating the robots on that exact same robots to do the data collections in, for example, folding this box. And human teleoperations is actually slower than human just using their hands to do these tasks, even if you have gone through, for example, hours of training. This is because you are just using a different embodiment than an embodiment that you person is the most familiar with. And also at the same time, because the robot arms are still certain distance away from you, there will be occlusion. Sometimes you have to look very closely, carefully, changing your heads, changing the viewing angles in order to really understand, is it the time to progress into the next task stage or not? There's a lot of caveats and inefficiencies of the current data collection regimes. That is why the policy directly trained on those data turn out to be slower than human speeds. So that's why there's a lot of investigations in how we can do those kind of data collections to be even more efficient, to be at human speeds. That is actually a very active research direction. So this is a very good question. So for this box folding task, I would argue this is already a very long horizon task. So I was very impressed by how good this one single policy is able to handle this long horizon task. But you could argue, if you really want this policy to be useful in some a more larger scale, in the wide scenarios, for example, in your home, you not only want the robot to fold the box, you want it to fold the shirts and clean the beds and clean all the messes on the floor. If in those type of scenarios, currently, me personally, I don't believe one gigantic policy is able to adapt to those scenarios. Some higher level abstractions or some kind of scene graph, some symbolic representations needs to be in place as a condition for this vision language action models, for those policy to be the most effective and useful to steer into different type of tasks and scale to larger scale environments and more complicated tasks. So this started with a pre-trained vision language models. So that's why there's already a lot of semantic knowledge that are learned through this large scale pre-training using this vision language data. So that is why some of these generalizations are coming for free, meaning the base model can actually have surprisingly good levels of generalizations at the semantic level. And it's just you have to fine tune this model with those robot data to making sure it can also generalize not at the semantic level, but also at the action level. So we can have the question maybe at the end because we are already about time. I still have the last 2-3 minutes. I will discuss some of the remaining challenges, especially along the developments of robot learning models. So one of the major challenges the whole community recognize is evaluation. Evaluation currently is primarily done in the real world. For example, this is a picture of Google Robotics. They have a grid of this kind of teleoperating Aloha systems that they are doing data collection and also evaluation. And real world evaluation is both costly and noisy. Their exact words to me was, for evaluation, they have large enough budget such that they can still make progress. This was their exact words. Meaning, if you were to do the evaluation or I were to do the evaluation, the results can be very different from each other, depending on how we specify the initial configuration and how the lighting condition might change. Even the friction parameters of the end effector can make a huge difference in how robust your downstream policy is. So this is very costly, and they have to wait for 2 days for the results to come back. And currently, there's very weak correlation between the training loss and real-world success rates. So this is another very important caveat and difference between supervised learning and also this kind of sequential decision-making, this kind of policy learning, is for supervised learning, your training loss directly measures how good your model is. But for this kind of policy learning, your training loss measures how good this one-step prediction is, which sometimes may not be, and actually often the times, is not indicative of the performance of policy over long task horizons. Even if your loss is low, but for long horizon task execution, your policy can actually be worse. And the training objective versus the task-specific metrics, like training versus task horizons, are some of the reasons explaining why it is very hard to come up with even approximate or proxy metrics to measure the performance of the policy. And people have to rely on real-world evaluations. So then the question is, what about doing the evaluation in the simulated environments? There has been a lot of investigation, for example, behavior, which is done in Feifei's lab here, also at Stanford, and also the Habitat 3.0 from Meta. People are trying to come up with these expensive simulated environments, trying to do evaluation and measurements of the robot policies. And obviously, there has their own issues, especially with regard to sim-to-real gap. How can you do very accurate simulation of rigid body, deformable object, and clothes? They have good correlations with the real-world performance. And assets is also another major issue, where large-scale generalizations and generations of those assets is a huge pain. I can't elaborate, but maybe after the lectures. And also how to digitalize the real world is an issue, and how to do procedural generations of realistic and diverse things are all issues of using simulation to do evaluations for robot learning policies. And really, we want to find a correlation between sim and real, and it's calling upon the ImageNet in embodied AI. The reason why ImageNet was successful is because, at least for a few years, any progress in ImageNet, meaning progress in deep learning and computer vision, we want the same thing. We won't have this platform, meaning any progress on that benchmark or platform, meaning progress in robot learnings. So that's something that we really want. And I can maybe skip through, we talk about how to build these foundational policies. There can also be investigations on how to build foundational world models. Especially now people are collecting large-scale action condition robot interaction data to train these foundation policies. But there's a lot of dynamics knowledge embedded in those data. If we just use those data to do policy learning, that would be such a waste. So we are also thinking about how we can use this large-scale action condition robot interaction data that was already collected to train those foundational policy, to train these foundational world models and how they can do interplay between each others. And there are some existing works that are thinking about along the direction of building this kind of foundational world models. And there are some very interesting characteristics you might thinking about, do you want it to be 3D? Do you want structural prior? How much learning versus how much physics? And how it can correlate with the real physical world. Maybe actually, I think we are about time, so I will end it here. And this is the future we hope to achieve, to really build this foundational robotic model that can work very widely and generalize very well in the unstructured data environments around us. And next lectures will be human-centered AI, and that will be the end of today's lecture. Thank you so much.